I'm talking about Signomial optimization, and probably, I'm not sure if you're all familiar with it. I should start with explaining a little bit what a Signomial is, right? So, very simple, a Signomial is a weighted exponential sum supported on a real set. So it has this form. So basically it is a weighted linear combination of exponentials of linear forms. Yeah, so the coefficients are real, the exponents are real, and an example of such a Signomial is given here. And Signomial programming is then just optimizing with these Signomials. So we want to, given a Signomial, we want to minimize this Signomial subject to a Signomial constraint set. And usually this is a finitely, it's a finite set of finitely many Signomial inequality constraints. And this value will be denoted with fk star. So in general, this is a non-convex optimization problem, and it is a fact that it's computational intractable. So it is NP hard. Despite that fact, Signomial programs have substantial applications. So particularly in aircraft design, it's a bit more historically, I would say it's applications in structural engineering, and since the 1970s, also chemical engineering. But the area that is right now really booming is aircraft design. So for instance, I brought you here an example of an optimal pulse pattern problem, where Signomial programming, and especially also the tools I present you today, was used to compute such a global bound for such an optimized pulse pattern problem. So optimized pulse patterns are, I would say, gaining increasing popularity in the power electronics community over the well-studied pulse width modulation due to their inherent ability to provide the switching instances that optimize current harmonic distortion. And here on the right, you see an example of a hyperloop design. So a hyperloop system is a uniquely coupled problem because it involves the simultaneously design of a complex high-performance vehicle and its accompanying infrastructure. And it turns out that this can be very nicely modeled into such a Signomial program. So these Signomial programs have various applications, but unfortunately they are NP hard to solve. So what can we do now? So first of all, we could maybe reformulate this problem a little bit to see if it gets then tractable. So first of all, we see that this is equivalently written as such a problem. So namely finding the largest real number gamma, such that f minus gamma is non-negative. So basically what we did is we took this optimization problem of Signomial programming, and I would say we have rewritten it in a more algebraic way that basically reduces the problem to the algebraic question of deciding non-negativity of a specific Signomial on a specific Signomial constraint set. This is a key problem in real algebraic geometry, especially for polynomials. This dates back to the 19th century and questions of David Hilbert and co. Yeah, but clearly, unfortunately, it is still NP hard. So you can see that very easily, since deciding non-negativity of a specific problem, which is somehow modeled by the co-positivity problem, can be modeled in such a way. So, and since we know that such a copositivity problem is non-negative, we know that this is also NP hard in general. So we somehow reformulated the Signomial program, which was NP hard, into another algebraic question, which is still NP hard. But now we can make use of techniques and ideas from the real algebraic geometry community and convex analysis. So the usual approach to handle such question now is to find outer and inner approximations of these sets. So maybe let me explain that a little bit more in depth to you. So the set of non-negative Signomials form a very nice geometrical object. We call it cones. And these convex cones, or basically this question about non-negativity can be restated then as a membership problem in this specific cone. And since this question is intractable, one is now searching for either outer approximations or inner approximations of this cone, where one can test membership more easily. And these cones are then described by so to say, by a Positivstellensatze, and we can check membership in these approximative cones more easily. A very prominent example for such an inner approximation of this cone for polynomials are sums of squares, right? If you think about a polynomial and you want to test polynomial non-negativity, I think it's rather clear that if I give you a sum of squares, so a sum of squared polynomials, that this is somehow the so-called certificate of non-negativity. And here, this membership problem can be reduced to semi-definite programming. In recent years, there are alternative certificates adapted to specific sparse settings. And here, by sparse, I mean that they preserve sparsity of the underlying structure. And these are called sums of non-negative circuits and sums of AMGM exponentials. So the first one that was first somehow introduced for polynomials, but then generalized also to this Signomial setting we are today in. And SAGE was basically directly for this Signomial setting. And most importantly, these two certificates can be detected by a convex optimization, namely via relative entropy programming and geometric programming. So let me depuzzle that a little bit for you. So these are, again, inner approximations of our cone of interest, where we can test membership via these two specific convex optimization problems. And what we want to do today is we want to find an approximation, such a conic approximation via so-called conditional SAGE. So we take the SAGE and condition it a little bit. All right, so the outline for my talk is as follows. So first I introduce you to the concept of Signomial rings. Then I provide some necessary basics of this SAGE and also what these conditional SAGE are. Then I present the Positivstellensatz respecting the Signomial rings. And then very interestingly, I show how by really grading such Signomials and rings, we can get a hierarchy, a complete hierarchy of lower bounds that converge to our optimal value of our Signomial optimization program of interest. And then I illustrate the practicability through a chemical reactor design problem. And if time allows, then I provide a very, very brief outlook on complete hierarchy of upper bounds. But let's see if really time allows to do so. Okay, so what are Signomial rings? So we start by considering a finite ground set A, and this finite ground set contains the origin. Then we associate to every vector inside our ground set a monomial basis function. So to say, this exponential function that takes these values. So the exponential composed with linear functions of a variable x. Then we saw earlier already that we can write a Signomial like so. So as a linear combination of our basis function e to the alpha x. And this a here is then the support. And the support is, as you probably all know for polynomials, is just the smallest set for which f lies in the span of our basis functions. A specific type of Signomials, namely when we only have non-negative terms involved, that we call Posinomials. So to say, if all C alpha here are non-negative. Then with that, we can define basically our Signomial ring as the R algebra generated by these basic functions. So that is basically the set of all finite products and real linear combinations of such basis functions. So for modeling reasons, and also very popular in the literature on geometric programming, Signomials are usually written in a different form, which we like to call geometric form, namely like so. And this looks aesthetically identical to a polynomial, I would say. And in order that this expression is defined, clearly the vector t has to be element-wise positive. And then you can think of Signomials as generalized polynomials, so where you allow for arbitrary real degree, at the cost that you restrict your function to the positive orthant. All right, so this is our setup. Let's now consider a specific Signomial. And since our optimization problem was reduced to the question of non-negativity of such a Signomial, the question is now, okay, how can we check Signomial non-negativity? And first of all, note there is one very, very easy case, the Posinomial case, right? Because if all coefficients are non-negative, then clearly, because the exponential function is non-negative, we know our Signomial is non-negative. That's great. So let's consider the, I would say, the next easy case. That is, if all but one C alpha is non-negative. So we have a Signomial with at most one negative term. What can we do now? So first of all, a notational or a nomenclature thing. So we call such a Signomial with at most one non-negative term an AMGM exponential, or for short, an H function. The name becomes clear in the next slide. So it turns out that using a convex strong duality argument, we can handle this situation very well, and it can be accomplished efficiently. So let's take maybe a look at an example. So here we have a Signomial with at most one negative term. Then we have exactly one negative term here. And the exponent vectors shall be given like so. Then we can basically see that this Signomial is non-negative via the following arguments. So first of all, we have this identity, right? We can exchange x and alpha. And also we can use convexity to bound the negative term, right? So we see that alpha 4 is a convex combination of alpha 1, 2, and 3 via this equation here. And then we can use convexity to basically reach this inequality, which says, okay, this Signomial is indeed non-negative. So this here provides a global lower bound on the convex function. And historically note that convexity is, or convexity of the exponential function is basically equivalent to the well-known AM-GM inequality. That's now also where the name comes from. So here, a reminder what the AM-GM inequality was, or basically this is the weighted form, right? So you can equivalently show this non-negativity via the AM-GM inequality. And then appealing to strong duality, that shows that basically certifying this inequality here can be accomplished in a computational tractable manner. Okay, so far so good. What if we have now more than one negative term? This is a very natural question. And also natural condition that one usually takes now is that we certify non-negativity by expressing this now as a sum of H functions. So we take H function as the building blocks, and then we take sums to somehow decompose a Signomial with more than one negative term as a sum of Signomials with at most one negative term. And clearly, as then each term of this, I would say, SAGE decomposition is globally non-negative, this is easily seen that SAGE functions are also globally non-negative. And this very general case can be checked via a convex optimization problem, namely relative entropy programming. So again, if we have more than one negative term, if we can write this Signomial then as a sum of H functions, we call this SAGE function. And I can check if a Signomial is a SAGE function via relative entropy programming. I don't want to get into more depth for relative entropy programming here. I think the most important thing here is that relative entropy programs are convex optimization problems, and they involve a specific constraint defining this relative entropy program. And this looks like so. And a very nice condition about this relative entropy constraints is that they are jointly convex in both its arguments. And we have a computational tractable barrier function for this cone, so we can compute nicely with it. So clearly, in general, this SAGE decomposition gives us only a sufficient condition for non-negativity. That is, there are non-negative Signomials which are not SAGE functions. And one such example is this Signomial here. So we have two negative terms here involved, and we see that this Signomial is non-negative by expressing it as follows here, like in the last line, because it's the square, so obviously it's non-negative. But unfortunately, this Signomial cannot be written as a SAGE function, so it cannot be decomposed into a sum of H functions. Okay, so that was the start. So this was, I would say, a normal SAGE. So what are we going to do now? We conditionalize this situation. So this duality argument we talked about also generalizes to constraint problems. That is, if we want to test non-negativity on a specific set X. And first of all, again, a definition. So we call a signomial that is non-negative on a specific set X and has at most one non-negative term. We call that an XH, right? So a normal H was just non-negative globally, and such an XH is non-negative on the set X. And I think it's fairly natural now that we can now take sums of these XH functions again as a condition to certify non-negativity on this set X for more than one negative terms involved, and we call such a signomial then X-SAGE. The set of X-SAGE signomials supported on a specific set A that forms, again, a nice geometric object, namely a convex cone. And we denote it with Cx of A. And like in the non-conditional case, membership in this cone can be tested by a relative entropy programming. And a very nice condition of such X-SAGE and also SAGE is that it preserves sparsity. That is, if I take a look at a signomial which is supported on a specific set A and that has k negative coefficients, then it is exactly X-SAGE if I can write it as an XH, as a sum of XH functions with exactly k negative terms, and each are supported on the same ground support set. So to say, we have a cancellation-free decomposition. And this is inherently different to, for instance, this usual approach via sums of squares in the polynomial case. But maybe if you're not so familiar with that, I brought you an example. So consider this function. This is a univariate signomial, so we only have x as the variable, and we have three negative terms, here, here, and here. And we want to check if it is non-negative to the left of the y-axis. So if x is smaller or equal than 0, so here. And clearly, by just looking at this graph, it's evidently non-negative over this set. And we can use the methods here to find the decomposition. And specifically, we have a numerical solver, SAGE, that does the job for you and finds, I would say, suitable round decompositions. Namely, it finds these three signomials, these three x h functions, and these are given here in color. So I will not provide you a certificate by means of that I'm not showing you that these FIs are really non-negative, that you have to believe me. But what I point out is what means sparsity now here. So there are two things going on here. So first of all, our input signomial, so to say, where we wanted to check non-negativity, had three negative terms. So we only require three summons for the decomposition of this signomial as an X-SAGE. And secondly, if you take a look at the different summons, say, for instance, here F1, this has clearly only one negative term because we want to have it as an XH function, right? But specifically, the only negative exponent that, or the only exponent that corresponds to this negative term is here minus x. So we don't have involved a constant term and also not a term supported on 3x. Yeah, this is what I meant with cancellation free. So we have a decomposition of this input signomial f as these three xh functions, where every xh function only involves one negative term, where this bad term, I would say, is supported exactly on one of these bad supports. All right, so I think now we learned the basics about this approach. So now let's talk about the Positivstellensatz we now want to use in order to get a hierarchy in the end, which approximates our optimal value. So the Positivstellensatz looks like this, and before we unpuzzle this, let me maybe first roughly explain what in general a Positivstellensatz does. So a Positivstellensatz is a specific representation theorem that tells you if a signomial is positive on a certain set, then I have a specific algebraic way to describe this positive signomial. This is in a nutshell, so to say, the key to approach these non-negativity questions, or at least the conditional non-negativity questions. And there are lots of different Positivstellensätze which differ by the exact representation of this positive polynomial or signomial. And so our Positivstellensatz goes like follows. So we have a constraint set, X. This is compact and convex. Additionally, we constrain it with signomials. So in total, we get the constraint set K. So to say we have a K is the intersection of a convex set and possibly non-convex signomials. So in total, it can be non-convex. Then the result is that if f is positive on K, then we can write f in a specific way. And the specific way we write the signomial then is like so. So it can be written as a sum of these lambda i's, and this lambda 0 is an x-SAGE signomial, and these lambda i's are posinomials, so signomials with non-negative coefficients, so very nice objects. And here are the constraining GIs involved. So it is basically a linear representation in the GIs with signomials or with x-SAGE signomials. And comparing this with previous Positivstellensätze, we can see features here are that we have no products of constraint functions. So the constraining functions here are really linearly involved in this representation. Then also none of these constraining sets, so X or also X for X, need to be semi-algebraic. So sometimes in previous Positivstellensätze that was an assumption one had to make. And also we don't make any assumptions on the signomial on the ring A, on the support A. So for instance, in previous Positivstellensätze there were regularity conditions like Archimedeanity or something like this. So we totally get rid of that. And one very nice corollary one can pose from that theorem is if we have no conditional or additional constraining GI, So we only have this compact convex set X involved with no non-convex constraints. Then this collapses to the very, I would say, easy to state argument that this signomial, so the signomial multiplied with a specifically large sum of exponential function is X-SAGE. This corollary in a little bit more specific form was known before. And I would like to highlight the differences here, namely the differences where are that previously one had to assume rational supports, whereas now we have reals. And something what will be clear or what will become clear later, namely that previously one assumed that this A-degree is 1. But like I said, this will be clear what that means later on. So we can see that our corollary nicely generalizes this theorem what one knew before in the literature. I want to briefly outline the proof structure here, but really only giving you the proof idea. So basically it is that since we have here Signomials involved and the real algebraic geometry literature is heavily dealing with polynomials, we do a little bit of mapping. So basically we map our Signomial situation to homogeneous polynomials. So via this map here, we represent our setup, so to say, in the polynomial world. Then we take care of some annoying subtleties, I would say. And if we have taken care of that, we can apply a Positivstellensatz from the real algebraic geometry literature. And then we take this decomposition we get from this Positivstellensatz and carefully map it back to the Signomial world. This shows the corollary, and this entire analysis is purely invariant with the support and also with this basically this constraint set X. So we can make then an easy extension to really get the general theorem where we additionally constrain with these possibly non-convex Signomials. Okay, now we have such a Positivstellensatz. Now we want to use it for optimization. So we have this representation now, and clearly we have to somehow grade now these certificates. So because of sparsity preservation, we know that these the support of this X-SAGE is purely given by the support of F. It will be the same, right? So this support will be the same as on the right-hand side, on the left-hand side. So we only have to take care of the support of this right-hand side. And the question is now, how do we move forward about this? Because inherently, Signomials do not have a notion of degree. That is something that comes from polynomials. If you will, you can think of, we measure the complexity of a polynomial with its degree, and the complexity of the Signomial is more measured in terms of the number of terms. But somehow we want to grade here something. So we want to come up with a notion that somewhat represents a degree for such a signomial. And this has to be somehow dependent on clearly the input signomial, then on this R, and also somehow dependent if we multiply something to this signomial. So there has to maybe change something in the degree. So we now came up with defining a so-called A-degree for signomials in the following way. So we define the A-degree of a specific signomial as the smallest number of products that I need to express f. So possibly I can take here non-distinct basis functions, but this is just the smallest number of products I need. And more formally, I introduced this set AD. This is the set of sums of at most d vectors from A. And then I can write my A degree more fancy like so. So this is the smallest integer d, such that the support is in this fancy set AD. Example. Let's consider this support set 0, 1, and 3. And we take a look at different signomials. So for instance, just x of x has A degree 1 because I have involved here 0. So I just, or I have involved 1. So I can just write this directly via my input basis function. So I don't need a product. The situation is different if I consider x of 2x, because then I would need the product of x of x and x of x. So I need two basis functions to express this polynomial and this signomial, and this. For the last one, I again only need one because I have as a support 3 involved. So a word of warning, so this notion is clearly not intrinsic to the signomial. So this is something really artificially imposed. And this is an artificially imposed concept to just handle this grading we want to have. And everything what is done earlier, you can somehow think of, we take just the whole support of f as our support, and then every signomial has a support, an A degree of 1. And maybe one structural thing, so this A degree is covariant really with affine changes of coordinates. So it behaves nicely under affine changes of coordinates. And with that, we define the ring of at most A degree D as this RA sub D. Okay, so we're almost there. So one thing that we found is namely that we have the following inequality about the A degree. So if we multiply two signomials, then the A degree is smaller or equal than the A degree of each of these F and G. And that is different compared to, for instance, polynomials. There we clearly have equality. But here you have an example where we really have this strict inequality. So if we have a support as this set, and then we consider a signomial e to the 3x, then this A degree of f is 2, because I need two basis functions to express my f. So for instance here, e to the 2 times e to the 1. And then every G, which has this form and gets then multiplied to F, the resulting Signomial has A-degree 1, right? Because the Signomial which is resulting is just C times e to the 2x. And since 2 is in my support, I have an A-degree of 1. So here we really have this strict inequality. That's why we define something what is called inverse support. And I think in regards to the time, I really skipped this specific definition. But in our graded hierarchy, I show you that this is just a notion or a definition to take care that nothing bad happens with the supports. Okay, but now let's come to our hierarchy. So here, what we wanted to do is we have a minimization problem of a Signomial subject to some Signomial inequalities, and we want to find this optimal value. And now we can, using our Positivstellensatz, find a hierarchy that is graded by this largest A-degree of the constituent Signomials. And this hierarchy looks like so. So we're searching the largest real number gamma, such that we have this representation. Every sigma 0 is a SAGE polynomial, Signomial with this support. And here these sigma I are posinomials, where with the correct support, that's where this inverse support comes in. And yeah, it turns out that this is a complete hierarchy. By that we mean if we now drive this degree higher and higher, we really approach our optimal value from below. And each of these bounds can be computed via relative entropy programs. All right, in the last maybe 2 minutes, I discuss an example of a chemical reactor design. So here we have a reactor exchanger pump system. And our goal is to find the best design of this chemical reactor system. So we optimize the design while meeting some criteria. For instance, we want to minimize the cost or we want to maximize the profit. And this leads to this really proper Signomial program, which looks like so. Yeah, so we have this objective function, and then we have a bunch of Signomial constraints. And first of all, we invoke the invariants in X to rescale this problem, because you see the coefficients in this original problem really span a magnitude of order 12. And so it's horribly scaled, so we make it a little bit nicer. And then we clearly have to choose a ring to work with our hierarchy. And here we choose the naive ring, meaning that we just take the support of F to be the ground set. And then you see we have here equality constraints involved. So what we do is we infer valid inequality constraints and push these equality constraints, because these are highly non-convex, right? Push these into our GIs. And then we tackle this problem with our software SAGE, which invokes also the numerical solver MOSAC. And we find that the first hierarchy order gives this bound, the second this, and we do solution recovery on the second order here, and we find that solution recovery yields this optimal value. So we see that the A-degree 2 SAGE relaxation solves our problem with a, I would say, 1% relative error. And clearly one can now apply global solvers from the nonlinear algebra, nonlinear optimization community in GAMS for that. And just maybe the overall takeaway is that SAGE produced the same solution as these solvers, but with a relative entropy program that could be solved in half the time as the fastest of these methods. And also, for instance, Skip was not able to handle any of this solution, and no bound was found before the timeout. And also only Lindo was able to certify really that our solution we get is globally optimal. All right, I think with that, in regards of the time, I should close. So I skip the outlook for the upper bounds. Here again, the take-home message. So we introduced a new Positivstellensatz that respects the structure of the new concept of these Signomial rings, and it's really the most general Signomial Positivstellensatz to date. From that, we derived a canonical hierarchy based on A-degree, and we demonstrated its hierarchy's practicability by several examples. So for instance, here we saw that's competitive with global solvers. And we also have an example that shows that it's much faster than in the polynomial setting than methods previously seen. And yeah, there's much more we did on this dual side. But yeah, I think I should stop now. Thank you.